Hey there! I'm thrilled to introduce our new GNSS interference detector, the GP Probe DIN L1. This device is a real game changer for the industry, and in this video I will explain why. Stay with me till the end, where I will announce the price for this awesome device. The detector is designed for installation in a DIN rail. It works on DC power ranging from 12 to 48 volts. There is a small color screen and some control buttons. Unlike our advanced 3-channel probe, this device has only one GNSS input channel, but it's enough to detect interference and signal anomalies caused by jamming and even spoofing. And next we have GNSS output. The signal from the input goes through an RF switch to the output. In case the device detects interference, anomalies or degradation in GNSS signal quality, the output is disconnected. This is a straightforward and intuitive way to integrate our device into your system. You can simply connect the device between a GNSS antenna and a receiver. Next cool feature, we have PPS input. So you can connect a PPS output of a time saver, for example, or a 5G base stations to monitor synchronization quality. How does it work? Inside the device we have a GNSS receiver with PPS and a module that measures phase difference between external and internal PPS. If the measured phase difference exceeds set limits, the device generates an event. Well, this means the probe combines multiple functions: interference detection, monitoring of GNSS signal quality, and measurement of time synchronization accuracy. Here you see a validated PPS output. What does validated mean? The pulse is generated only if there are any issues with GNSS signal. Well, it's not a time saver with a built-in high stability reference oscillator, but it's still a useful feature. There is a LAN port for network connection. Then we have a relay that switches when an event is detected. And that's, by the way, the easiest way to integrate the device into a system. But what if you need to control something more complicated? For example, controlling a camera when interference is detected, or sending a command to a time saver to go into holdover. For this purpose, we have a RS-232 interface. Since each device has its own remote control protocol and logic, we have integrated the Lua scripting engine into our device. This enables implementation of any algorithms for responding to interference. Like our advanced sensor, the probe is fully compatible with GP Cloud. And here we come to the most important feature of the device. It's the embedded interference detection. This software option is called OSP, Onboard Signal Processing. And now I will demonstrate how it works. Let's log into the built-in web panel using admin default credentials and start with a brief overview of the user interface. Here we see the device current configuration page. Right now we see that the probe is connected to GP Cloud. Next, this is the measurement configuration section. We can see the enabled constellations and two data processing options: cloud-based or on-board with OSP option. This is the connection setup. It looks pretty standard. Settings for accessing the GP Cloud API, IP settings, and here you can enable SNMP agent. On this page you can define rules for disabling output ports and for switching relay. This means when the device detects interference or anomaly, the port disconnects. It's a basic but very effective way to integrate the device into your system. Moving to administration, we start with licenses. There are two software options available for the device. The first one is OSP, which enables onboard interference detection. The second option is Lua. This is an integrated engine and debugger for custom scripts development. Here we can see different ways to activate a license, with or without connection to internet. Here you can change the default passwords for admin and user. And this is the Lua script debugger. I will show you how to use it in one of our upcoming videos, so don't forget to subscribe. This particular script that you see on the screen outputs the past and current status of the device to the COM port. On this page, we can update the device firmware in various ways. Download from the GP Cloud server or from a local disk. And the final menu item is rebooting the device. Let's see how the built-in interference detection algorithms work. Let's activate the OSP function. Go to Measurement Config and switch data processing to OSP. And go to Status, Measurements. Here we see spectrum waterfall and power spectrum, anomaly probability, and trigger threshold of 50%. When the sensor detects anomaly in the GNSS signal and the probability exceeds a threshold value, the device shows anomaly status and logs the event. This logic applies to the other graphs as well. For example, when the peak power exceeds its threshold, the device detects interference. The same goes for horizontal position accuracy and PPS offset. Next, we have charts with additional data such as signal-to-noise ratio, number of visible satellites, and residuals. Similar to the GP Cloud user interface, you can zoom in and out on the charts using a mouse scroll. This is really cool to use. I'm going to generate interference using Adalm Pluto SDR and our new software called GPS Patron Interference Lib. Let's select a broadband signal with Gaussian noise modulation with a bandwidth of 5 MHz. Let's go. You can clearly see the interference on the spectrum waterfall and power spectrum. On the anomaly plot, we can see 100%. Also, the peak power has crossed the threshold, so this incident is classified as interference. Here we can observe the degradation of signal-to-noise ratio and increasing residuals. Let's stop the interference and see how quickly the device recovers. Excellent, the sensor is showing normal status again. Finally, let's take a look at the last page. Here we have a list of registered events. This is our newest one. We can see the start and stop time, duration, maximum power during the incident, and spectrum width. And you can download this entire list to your local drive. Well, as you can see, our device is incredibly functional. Let's summarize. It can work offline without internet connection. It offers a wide range of integration options. It can be connected between a GNSS antenna and a receiver. It enables monitoring the accuracy of time synchronization. And in combination with GP Cloud, it records the quality of GNSS signals. A lot of features in one compact device, right? Now about the price. I believe that a robust GNSS should be available to everyone, not just for military with huge budgets. That's why we have made available two versions of the Evolution Kit. The base version with minimal options is available for only €399. And the maximum edition with all options is available for €799. To order your unit, please visit our website at gpspatron.com, browse for GP Probe DIN L1 and select the product version and software options most suitable for you. Thanks for watching and see you next time.